So yesterday we were working on expressing equations of lines in 2D and 3D. So vector equation, we learned about parametric and symmetric equation. Today we're going to move forward and see how we can express a plane in 3D and what that equation looks like. But just as a little recap from yesterday, in order to express a line, we usually will express this with 1 point on the line and also a direction vector, which is parallel to the line, and that essentially just kind of tells us what direction that moves in, crossing over that 1 point. So as your point, we will turn this into kind of like a position vector. We called this R naught yesterday. You may have also noticed that the textbook calls this P initial or P naught. Brian? No. So you can use either. Well, the line crosses through both, right? So both of these are points on the line. So I can use point A or point B. And essentially to decide on my position vector here, I can do the vector from the origin to point A, or I can also do OB. And this will be our, we'll go with the textbook and we'll say this will be our P naught or P initial. So essentially we get the vector that goes from 0, 0 out to point A. So that's our position vector. I also want our kind of like a slope vector, but we call it a direction vector. And this can be, we can have a couple of different answers for this too, depending on whether we do AB or BA. It doesn't really matter, I can do either. So let's just suppose we do the direction of AB. So I want to do tip components minus tail components, so it'll be 5 minus 1, 1 minus 2, and negative 3 minus 0, giving us the direction vector 6, negative 1, negative 3. Okay? If you happened to have done BA, that's okay. You would have just gotten this same vector, but the signs reversed. So that is also another option. Okay? So when we create our vector equation of our line here, we're going to say R equals, and we'll just do this. And we'll have our position vector. And then we have our parameter. Usually we use the value t. If you're doing this on a graphing software like GeoGebra, it's lambda. Doesn't really matter. And then we'll have that being multiplied by our direction vector there. Okay? Essentially the t, the parameter t, just says it can be any scalar multiple of our direction vector, or all scalar multiples of our direction vector. So this is the vector equation of our line. The question also asks us to set up parametric and symmetric. So for parametric, what'd you guys get for your parametric? I'll ask you. Someone set those up?
Mine.
Go ahead, Aiden.
A1 plus 2AE, 2 plus 2T, and negative 2T.
-1 plus 6t, right?
Yeah.
Okay. Yep. Yeah, negative 3t. Okay, perfect. So that essentially just comes from setting up our components here. So I'm going to set up the x parts of it, and then I set up the y parts of it, and the z parts of it. So kind of just like focusing in on these 3 pieces of information. And then how did you guys get your symmetric equations? What's that? Rearrange for t in each thing, and we set them equal to one another. So if you imagine, I don't think I need to show the isolation at this point, but if I move the 1 over, it's x plus 1, and then I divide out 6, so x plus 1 over 6 should be equal to y minus 2 divided by negative 1. Okay, this I would probably simplify just a little bit, and then z over negative 3 gives us z over 3. You don't have to necessarily do this, but when we divide by negative 1, I think we could just express that as like negative y plus 2 or 2 minus y, just because I don't think it's really necessary that we express something with a division of negative 1. But again, not a big deal. So there's our symmetric. And these are our parametric. Okay, any questions? No? We're all good? Okay, so I want us to think about a plane in 3D space. So we can imagine that a piece of paper is our plane. What would I need for this plane to be defined in space without being wobbly? Okay, so let's imagine we have, I don't have marbles, and it would be hard for me to hold all of them anyways, but let's imagine we have one marble, and it's just in space, right? And if I have one marble, is my plane laying flat on that? No, my plane can kind of rotate around. How about 2 marbles? Can our plane still wobble? Yeah. How about 3? Okay, so 3, when I have 3, if you look at my hand here, that basically defines our plane, right? Those 3 points mean that I can't rotate my plane anymore. If I only have 2, that's essentially a line, and my plane can still wobble on that, right? But if I have a third, then all of a sudden my plane is defined in space, right? Hayden?
What if all 3 points are parallel on one axis?
So they have to be non-collinear points. Yeah. So we know any 2 points, of course, can make a line, and those would be collinear, but the third one cannot be collinear. Yeah, so good point. So I can have 3 points that are collinear, or if I happen to have 2 lines and a point, or like 2 direction vectors and a point, that would also work, because I can get my direction vectors from a set of 3 points, and then I can have an additional point on there. All right, so we need either 3 non-collinear points. Now I'm trying to remember if collinear has 2 L's. Yes? Okay. Yeah, you're right. Okay. And essentially from 3 non-collinear points, we could also get, and what we will do is we'll get 2 direction vectors that kind of like show how 2 of those points are connected, and then a third point to make sure that that's defined. But if we happen to already have 2 direction vectors that are not parallel to one another, we don't want those to be like parallel, because again we have that tipping problem, and then a third point. So we can have 2 non-parallel direction vectors. And 1 point. Okay, the thought behind this is essentially when I express direction vectors as vectors, we express them heading from 0, 0 to the tip of like a particular point, right? So if I have these and they're right at the origin, they're coming out from the origin, these can technically be slid anywhere over my 3D plane, like my XYZ plane, or I should say XYZ coordinate plane. So I need to know where this plane stops. So if I have those 2 direction vectors, I know kind of like how the plane lies in 3D space. I just don't know where it lies in 3D space. So as soon as I have that point, my plane stops moving, right? And I know exactly where it is in 3D space. So I need those 2 direction vectors, but again, those direction vectors can still move technically because we're expressing them from 0, 0 to a particular point. They could be anywhere though. And then I need that point in space to decide like, okay, it lands here, right? From those direction vectors. Aiden?
If they're Cartesian vectors, then wouldn't it just be from the point, like at the origin?
Yes. So keep in mind though, like if I had the point, let's look back at our warm-up question. This is a good example. When I have this, and I have the point going from A to B, when I figure out this vector right here, this is the vector that starts at 0, 0, even though it's not necessarily at that location in 3D space. So I need the point to decide where that is in 3D space. Yep.
I understand why the 2 vectors couldn't be collinear, but why couldn't they be parallel?
So if I have like parallel vectors and a point, let's say my point is, just trying to think of a good example here. If I have my point over here, so when you have two parallel direction vectors, that means the points that you used on those are collinear, right? Right? The points on this lie on the same line, right? So we have this problem where, again, when I have these two direction vectors, it actually doesn't tell me where this plane, how it rotates in 3D space. That's kind of the point of the direction vectors. When I have two direction vectors, sorry, I know that this is like not the ideal way to show, but when I have two direction vectors and they actually form a plane, right? Like this doesn't form a plane. They're kind of the same. But when we express them, it doesn't matter if they're further apart or not. It still doesn't define where this rotates in space. Yeah. Okay. So vector equation of a plane is very similar to vector equation of a line. We are going to have, let's say, actually I don't know if I have something underneath this or not. Maybe I do. Hey, there we go. So I'm going to have my R and my R naught or P naught, whatever you want to call it, plus the first direction vector with some parameter T, plus the second direction vector with some parameter S. Now, if I have a direction vector, and Mark, this probably answers part of your question as well, because if I have two of the same direction vector, when they're collinear, that's actually creating the equation of a line, right? If I have a direction vector and a point, it's actually just telling me like, oh, this is the line in space. So we need those two direction vectors to kind of like first define the surface, and then the point defines where that surface falls in 3D space. Okay, so essentially what you'll see is you have the x, y, z coordinate of your position vector. Okay, so we still want one point on the plane, and then we will create two direction vectors, and this will go for either one of these two cases. So if I happen to have, if I'm given 3 points, let's say, I'm going to create those two direction vectors out of my 3 points that I have available to me, and I'll choose one of them as my position vector point. Okay, so this is going to be our position vector. Okay, this will be our first direction vector, let's say direction vector A. This will be our direction vector number 2. Called B. And essentially, again, these S and T values are just parameters saying it doesn't matter the length of the direction vector. It can be any length. So T and S, we call these parameters. Just saying we can have any scalar multiple of our direction vectors A and B. Can I flip? No? Okay. Let me know when you're ready. Good? Okay. So this is like a classic create the vector equation. This one asks us to write vector, should have a comma there, parametric and symmetric equations for the plane in 3 space that passes through these 3 points. We'll just throw some labels in there for these points just for the purposes of our notation so we know what's going on. So let's just say we'll call these ABC. And we are also tasked to reduce any direction vector to lowest terms. What this allows for us to do is essentially just have a common way in which we're all going to express our plane, just so we don't have like a bunch of different answers. So we'll reduce the direction vector. If it happens to be, let's say I have the direction vector 2, 2, 2, I'll reduce that to 1, 1, 1, right? Same direction. Okay, so why don't we start with a position vector? PO or RO, whatever you want to say. I'm just going to use the first point that we have. So this is going to be the point OA. What is that? Oh. Is it like Pop Rocks?
Oh yeah, it is.
I thought your water was spilling.
Wait, did you put it into the water bowl?
Just for fun.
Okay, so I can choose, for my 2 direction vectors, I can choose any 2 points for each of them. Of course, not the same 2 points. Like I don't want to do AB and BA because those are collinear. But I can do AB and AC. I can do AB and BC. I think that's all the combinations. Or whichever order. I just don't want to do like AB and BA or anything like that. Okay, so let's just say for our direction vector A, we'll do the vector that connects A to B, which means I'll do 2 minus negative 1, 2 minus 3, and 1 minus 4. Giving me my first direction vector, 3, negative 1, negative 3. Is this fully reduced? Does this share any like common factors or anything like that? Okay, so I can't reduce that, so it's already fully reduced. Let's say for direction vector B, maybe I choose BC. And we do the tip components minus the tail components. Okay, I'm doing this quick because I assume that we know how to do this. Oh, sorry. I put 4 minus 2 equals 4. Should be negative 2, 2, negative 2. Ryan? So these are our 2 direction vectors that we get. So this is how we express the vector equation of a plane. We do 1 point and 2 of the direction vectors on that plane. Can this be reduced?
Yes.
2? Yeah. Great. Okay. Why can I reduce this vector without it affecting the equation of the plane? It's the same direction, exactly. So if I have negative 2, 2, let's just say it's like this vector in space. Negative 1, 1 is like down here, let's say. Okay? Okay, so from there, we can just create our vector equation. We'll say our position vector, and then plus our t parameter times our first direction vector, plus our s parameter times our second direction vector. Okay, again, could it be possible that we get slightly different equations? Of course, because I can choose any 3 of my points to be my position vector. I could also have opposite vectors to these ones. So I can have negative 3, 1, 3, and 1, negative 1, 1. Sarah, I almost called you Rebecca.
So for vectors to be like they need the first 2 need to be collinear, right?
No, we want our direction vectors not to be collinear. So if you had, so essentially like the points, the 3 points have to be forming kind of like a triangle, right? I don't want my points, or not even necessarily a triangle, but I can't have all 3 in a line, because if I have all 3 in a line, I just have a line. And then I don't know where that plane lies in space because the plane is wobbling on that line, right? So in order for me to have a plane that's actually defined, I need those 2 direction vectors to not be parallel, essentially.
So you place like A, B, and B, C.
Yeah, it doesn't matter.
But like there's like those just like those combos like A, B, and C.
I just don't want to choose like AB and BA, because that's the same line, right? Okay, so this is our vector equation. Could someone set up our parametric equations for us?
Is parametric like the X, Y?
Yeah.
Like
Okay. -1 plus 3t minus s, y equals? Perfect. And z? Great. Okay, so this question also asks us about symmetric. How would we set up symmetric equations here if I'm trying to isolate for the parameter in a symmetric equation? So the goal of symmetric is isolate for the parameter. Can we do that? Can I isolate for one of the parameters? Vincent, what do you think? We will do that eventually with some of these planes, but because there's 2 parameters, I can't isolate for the parameter, right? So there's actually no symmetric equations when we talk about equations of planes. So this is not possible with 2 parameters. Oh. Okay, therefore there's no symmetric when we're dealing with planes.
Is a plane just like an object? If we do
A plane is a flat surface in space, like this paper, right? Okay, just so you guys get a feel for kind of, I know I haven't shown you any visuals yet. This is a plane in 3D space, right? So we're defining this with 2 direction vectors, and I put the same point on these 2 different direction vectors here, so you can see that I have that information kind of all in there. But you can see that the plane lies flat on those 2 lines. So this is kind of what we're talking about when we're talking about creating an equation of our plane. The point I used was 0, 0, 0. So it was the origin. Okay. Any questions so far? Okay. I'm going to suggest for this one that you separate your paper into 2 sides, just so that you can save some space here. We'll do maybe like A and B on one side and C and D on the other. Okay, do we need a 2-minute break? I feel like you guys are... Okay, let's take 2 minutes here. Yeah. So I have actually set up, just so you guys can see a visual of what we just did, I've set up a couple things for you here. So I'll show you what I started with. I started with our 3 points, A, B, and C, in 3 space. So you can see that A, B, and C kind of lie, C's below the XY plane, and then we've got a couple of points. So if you imagine a plane falling on top of all of these, with my hand here, I can kind of just show you like, okay, so it's gonna lie flat over these guys right here, right? So I actually just use, like you'll notice that the equation of this plane is slightly different than what I just showed you because there's a couple different ways that we can express equations of planes. So when I went over here to my tools here, I just said that I want a plane through 3 points. And I clicked on those 3 points and it made me the plane that falls on those 3 points. So everyone sees how these 3 points, firstly the 3 points are not collinear, meaning that a surface can rest flat on them and not be wobbly, right? I can see that the plane goes through all of those, right? Now I'll show you what the point of the direction vectors are when we express this as a vector equation. So I wrote down here, you can't see them yet, but I wrote down here the 2 direction vectors that we found in our question. So we found 3, -1, -3 by doing AB, and -1, 1, -1 by doing BC and reducing it. And you'll see when I throw these up here, these are the vectors that start at 0, 0 and go out to these points, right? So what do you notice about these 2 vectors when we look at this kind of from the side here? Yeah, they're both essentially parallel to our plane. So imagine that this plane can move all the way this way or all the way that way. I don't know exactly where that lies with those 2 direction vectors until I also define my equation with one of the points, at least one of the points on the plane, so that I know, okay, it has to be parallel to these 2 vectors down here, right, as we can see. But then I also need to know where it goes in space. So as it's going kind of back and forth here, if you imagine it freely moving, I wish I could kind of like move it here, but if you imagine it freely moving back and forth, still being parallel to these 2 direction vectors, the only thing that I need at that point to define that plane is at least 1 point on the plane, and then it knows where to stop in space. Ryan?
So we could extend it in that direction.
Yes. Yes, so this plane does technically expand
Directions.
all directions, yeah.
How can they extend it in the y direction?
The y direction is just like this way. On the,
Oh, y direction is down.
the y direction is, this is our,
Which way you're like showing that?
sorry, this is, the green is our y-axis, so it means it's just like extending this way.
Oh, wait, I was looking at.
Just imagine it extending in all directions forever. Zainab? Okay, guys, shh, stop talking. If I move the points, I'm what? So I'm saying, suppose we didn't have these 3 points. All I know with these 2 direction vectors is that my plane, is that my plane has to be parallel. That's all I know. So I'm just saying, like, it could move back and forth this way and this way, as long as it still remains parallel to those direction vectors. But as soon as I know a point on that plane, then I know where to stop the plane in 3D space. Okay? So this is essentially what we know from our vector equation, the one that we set up. Those 2 direction vectors and then a point on the plane. Okay? All right. Let's go to the next one. So separating your page out into 2 here, we'll do A and B on the left. I'm just going to do mine in a row because I have a digital page that extends forever, like a plane in space, you know. We are going to determine the vector and parametric equations. The nice thing about this, Ryan? Shh. The nice thing about this is that it gives me the direction vectors. So it actually tells me the two direction vectors and the position, the point. So I can simply, I'm just going to show you another way that sometimes we express a plane and sometimes it's like this. You can also call it some vector. But sometimes you might see this, just so you're aware. And I'm going to have the position vector plus my 2 direction vectors with their parameters. So that's our vector equation. Parametric, we are going to separate out the x, y, and z coordinates as we have before. So x will be 3 plus 8t plus s. Y will be 7 minus 5t minus 3s. And z will be 0 plus 4t, so I'm not going to put the 0 there, plus 2s. Rachel. Yes, sorry. Thank you. Oops. Okay, the second part of this asks us to check if point Q is on the plane, so -10, 8, and -6. There could potentially be a couple ways that we could solve this. We could try to guess and check for parameters of S and T and see like if we can find that this point lies on the plane. The problem with that is that S and T don't necessarily have to be whole numbers, they can be fractions. So if my S and T are fractions that make that point Q fall in that plane, then I have an infinite number of answers that I would have to try and guess and check with. So the only way to know definitively is we're actually going to use our parametric equations, the x, y, and z here. And I'm going to actually plug in the x, y, and z into our equations. And then we'll have to do a little bit of what Vincent suggested, which is like elimination to check if we can get a true statement. Okay, I'm going to simplify these guys out just a little bit because we have constants over on these sides as well. So I'm just going to move these guys over so that we have more simplified versions of these equations. So I'll have -13 equals 8t plus s. 1 equals -5t minus 3s. And this one will stay as it is. So just simplifying a little bit there. Okay, so let's just say we have equations 1, 2, and 3 here. Here's the goal. We have 3 equations and 2 unknowns. We should be able to solve with elimination in a set of 2 and plug that into the third set and try and solve for the last variable that makes this true, if it is true. So if you get something that makes sense, in other words, I can use elimination and find an actual t value and then plug it in and actually find an s value. If you get something like that, that means the point lies on the plane. If you get something weird, like we try to solve for elimination and then we get like 0 equals 0. You guys remember some of those scenarios back from grade 10? That probably means that the point doesn't lie on the plane. So we're just looking for essentially something that makes sense, right? So we're going to solve using elimination. Let's say we just use equations 1 and 2 for now. And my goal here is to eliminate either the s's or the t's. So I need the s's to have the same scalar or the t's to have the same scalar. What would be the easiest thing to eliminate? The s's. So if I do equation 1 times 3, that will set me up really nicely to be able to eliminate the s's out of these equations. So I'm going to get -39 equals 24t plus 3s. So just multiplying each of these values by 3. And then we're just going to set them up and make sure we line them up well so that when we add or subtract them, we can see easily what's happening. So if I have a positive 3s and a negative 3s, should I add these two equations to eliminate the s's or subtract them? Yeah, we'll add them, because then I'll get 0 for the s's, so those are gone. I'm going to get negative 38 here and 19t here. Okay, so I think this is getting somewhere where it makes sense. If I divide out 19, what do we get for t? Close. Negative 2. Okay, our last step is to consider this third equation, and we're actually going to sub this in to 3. So sub into your last equation to solve for s.
Does it have to be equation 3?
Yeah, it has to be the third equation that you haven't used yet. Okay, so what we're going to see here is eventually I want to see if this makes sense once I solve for the s equation, or the s value. So I'm going to get here negative 6 plus 8 over here. That will give me 2, which tells me that s is negative 1. Oh, sorry. Actually, you know what? We're going to sub this back in. Sorry, this is my mistake. We're going to sub this back into one of the two that we've already used, and we check it in the third one. Sorry, I jumped ahead a step. Sorry. You can do 1 or 2, and then we check in the third to make sure it makes sense.
So s isn't negative 1?
No, sorry.
Anyone have white
You're writing your lesson in pen?
Never make mistakes.
You're right. I'm so foolish.
Does anyone know?
Yes, Ryan?
Mary?
Why can't you sub it in number data? Wouldn't that make more sense?
Well, we're solving with elimination to solve for s and t in the first two equations, and then we're going to sub them both into equation 3 to see if we get left side equals right side, and that tells me whether the point is on the line or not. So we solve for it in the first two, any first two, and then we check in the third once we have both parameters. Okay, so our check is done in the equation that we haven't used. So we're going to check it in equation 3. So I am going to see when I plug in my supposed t and s parameters into equation 3, I want to see if I get left side equals right side. Okay, so you'll see here we get negative 8 and negative 6, which gives us negative 14. So does this point lie on the plane? No. Okay. So essentially, we want to solve for the two parameters in 2 of the equations and check it in the third. And that will tell us for sure whether the point lies on the plane or not. Does that make sense? Okay, so either I get a true statement, it can be 0 equals 0, let's say it's 2 equals 2, whatever. That means it lies on the plane, or I get an untrue statement like this that doesn't make sense, and then we say, no, it doesn't lie on the plane. Okay? Parts C and D. Part C asks us to find 2 points on the plane. This one is a lot easier because literally we can just kind of like plug things into the equation and see what we get. So you are just going to choose arbitrary parameters for S and T, and that will generate various points on the plane for you. So if I want to find 2, I'll do it 2 separate times. So I'm essentially, let's just say for the first point that I want to find, other than the position vector, or the position point that it gives me, let's just say we throw in 1 and 1 for this. So my x, y, z is equal to our position point, which was 370, plus 1 times 8, negative 5, 4.
How is S and T were the parameters?
Yeah, they are. So I'm choosing values for the parameters.
Is it better to do it in parametric? Because you can just plug in like 1 and just solve the x?
Yeah.
We do either.
Same thing.
Okay.
Yep. Yep, so if you wanted to plug them into your parametric and solve for the x, y, and z, I kind of think like here I'm doing 3 plus 8 plus 1 anyways, like it's all kind of together for us, so it doesn't really make a difference. But I'm going to get 12, 2 minus 3 gives us 1, and then 4 and negative 2 gives us 2. So point on the plane. Being sure that I distinguish between this position vector out to the plane and an actual point on the plane, which we do with our round brackets. So a point on the plane can be 12, negative 1, 2. And then we're going to choose 2 others for our second point.
Can we choose 0 for both of them?
No, because that gives us the position vector, which we already have that point. Okay, let's say we choose s equals 1 and t equals 2 this time. Okay, so I'm getting 3 plus 16 plus 1, so 20. I'm getting 7 minus 10 minus 3, so negative 6. And 0 plus 8 minus 2, so 6. So the point on the plane, this is the position vector out to the point. The point on the actual plane is the point with round brackets. Any thoughts for how we could find the x-intercept of the plane?
So x equal to 0 and then substitute from another.
Close. Okay. So if I just kind of like take a look back, guys, let's focus in here, please. If I take a look back, I know this isn't the same thing. This is the one that we worked with before. But if I take a look back here, any point on my x-axis, gentlemen, any point on my x-axis is actually where z and y are equal to 0. So the x-intercept means z and y are equal to 0. Y-intercept means x and z are equal to 0. And z-intercept, x and y are equal to 0. So just like when we're working in 2D, when I have an x-intercept on the x-axis, the y's are equal to 0, right? This time, just we add the z component, and the z is equal to 0 as well. So the first kind of starting point, if we're doing part D here, asking what is the x-intercept of the plane, it can be maybe useful for this one to use our parametric equations, because I know that I have, like, this is my x, and then I'm actually going to set the y and z equal to 0 in the other 2 parametric equations. So we have like 7 minus 5t minus 3s and 4t minus 2s, like we had above. Okay, so x-intercept means we set y and z equal to 0? Okay, and then Aiden had a good process going forward here. So if I can use some elimination now in these two equations here, I don't know, I can't use this x equation because I have an x here that I don't know. But if I have two equations and two unknowns, I should be able to use isolation to solve for those things. Yep.
What if you isolated,
Or isolation, substitution or elimination, sorry.
what if you like isolated for C and then isolated for S and then plug both of those into the first equation?
I'm still going to have two unknowns though, right? So this is what I can do. I will be, shh, guys. I will be choosing either an S or a T to first start with elimination here. So I think either way, we're going to have to multiply both equations by something. So any suggestions as to what we should multiply these guys by so that we can eliminate? Do you guys want to eliminate the S's or the T's? I think S's are probably easier because they're a little bit smaller. So we'll multiply this guy by 2 and this one by 3. Okay, so remember when we're using elimination, and guys, we're actually going to do this quite a bit using elimination in this chapter. So polish up on your skills if you need to. I want the S's or the T's to be the same, or opposite, I guess. Like I can have positive 6 and negative 6. Now if I want to eliminate a negative 6s and a negative 6s, do I add the equations or subtract?
Subtract.
We're going to subtract them. Okay, so I'll get negative 14 equals negative 22t. And the S's are gone. Okay, and then when we solve for t, we're going to get negative 14 over negative 22. And I'm just going to reduce that to 7 over 11. Okay, we are going to sub t into, let's say we call this 1 and we call this 2. We're going to sub it back into 1 or 2. Doesn't matter which one. Choose the easier one. Maybe we'll sub it in here into 2. So that we can solve for S. Okay, and then when we divide out that negative 2, the negatives cancel, and we're left with 14 over 11 for S. Okay, and we'll call this one our third equation, simply because that's the last one that we're going to use. So my job now that I've isolated for the S and T that make these two equations true is I'm going to just sub these back in for S and T in equation 3 and find the X value that works for that. So this is the last part. So we have X equals 3 plus 8 times 7 over 11 plus 1 times S, which is just 14 over 11. So here we would have like 33 over 11 plus 56 over 11 plus 14 over 11. So let me know what you guys get for that. Great, 103 over 11. So the actual point itself, the x-intercept, is the point where we have 103 over 11 and then 0 and 0, right? Good question. If there were no x-intercept, again, we kind of get something that's not making sense for setting y and z equal to 0 and trying to solve. So you might find that they both get eliminated or something like that. The only time that you're not going to have an x-intercept is if you have, yeah, something that's parallel to the x-axis, right? Thomas? Yep. Is this good? Okay, so I'm going to give you guys a couple seconds. I would like you to try example 3a and see if you can come up with the vector equation and the parametric equation for the plane that has x-intercepts at, or an x-intercept at 2, a y-intercept at 4, and a z-intercept at 5. Okay, so see if you can start with that. You did? Perfect.
I hate writing in pencil.
Okay, so this is what you're just going to do 3a. And if you're watching the video lesson right now, you can pause it and try it out. So I have just shown you guys what these look like as full points. So x-intercept, y-intercept, and z-intercept. I've labeled them A, B, C. I chose A as my position vector. You can use R naught or P naught, R initial, P initial, whatever you want. And then I used, for my vector A, I used the x-intercept and the y-intercept. And then for my direction vector B, I used my x-intercept and z-intercept. Mark?
Wouldn't we reduce AB?
Yes, so you can reduce AB to -1 to 0, for sure. And I can't really do anything with vector B because it's 4 and 5. I don't ever want to reduce a position vector. Mark asked me about that because this is actually telling me how far out to the plane we're going. So if I reduce that, I actually move my entire plane from like out here to in here. So I don't want to reduce that position vector, but direction vectors I can reduce, right? They're just scalar multiples of one another. It doesn't matter how long those things are. Ryan?
So if you're given the position vector, you can automatically assume the only two direction vectors.
No.
Easier for the last one, without the position, add big A to the position vector.
Yeah, and it gives you the 2 direction vectors as well. So either, the options are either you're given 3 points or you're given the 2 vectors and a point, or maybe you're given some additional information. Like in part B here, it gives you a different set of information. So I'll kind of show you how we can pick out information from that. Okay, so final vector equation here. You can use R, vector R, you can label it whatever you want, or you can use X, Y, Z. We're going to do 2, 0, 0 plus T times the first direction vector plus S times the second direction vector. Okay? And you might have something slightly different depending on what you chose to do. And then so that's our vector equation, and our parametric are going to be 2 minus T, 2T minus 4S, and 5S. Okay, part B, this is our final little piece here. Part B asks us a different type of question. It says the plane, I'll just scroll up here, the plane containing this particular line. So if I know the plane contains this line, I know it has this point, and this actually gives me one direction vector on my plane. And I also know it's parallel to this second line. So what does that tell me in relation to what I would need for my plane? Yeah, it actually gives me the second direction vector here. So it's important for us to remember that if the plane is just parallel to this line, the plane does not contain the point 1, 7, -4. It only contains the point that's contained within the line that actually is in the plane itself. So it contains this point, this direction vector, and it's parallel to this direction vector as well. So I can use this direction vector here. Okay? So I'm going to use, we'll use this as our R naught or P naught, whatever you want to use, is the point from the first line, and then my direction vector from the first line. And I can use my direction vector from the second line, but I cannot use my point from the second line because that point is not on our plane. Okay, so when we set up our plane, you can say vector R or X, Y, Z, whatever you want. We're going to have this. Oops. Okay, so there's our vector equation. And then we're going to set up the parametric. There we go. Okay, so you may sometimes be just given some general information about your plane, like it's parallel to this and contains this line or whatever, and then your job is to create those equations based on the knowledge that you have. Tomorrow we're going to talk about this equation. So if you guys noticed this equation when we were looking at GeoGebra, I typed in these 3 points and I got this equation out for the plane. So we're going to kind of talk about how we can express planes with equations like this called scalar equations. Okay? So we've got like 6 minutes here. We are working on 451, numbers 1 to 20. Let me just stop the video here.